Hi, I'm Kristin Persson. I'm the director of the Materials Project, and I'm happy to be here to talk about our software infrastructure for data production, dissemination, and analyses. The Materials Project is supported by the Department of Energy, Basic of Energy Science, Material Science Division core programs, and the spectroscopy data that I'll be showing just a tiny bit about is supported by the NSF Data Infrastructure Building Blocks program. The Materials Project was founded in 2010-2011. We went online in 2011. We centered the mission around 4 fundamental building blocks. Production of code that would allow us to produce materials property data in a robust, reproducible way, to save all the metadata and the provenance and the results in databases, to disseminate that data in a way that is comprehensible for people that are not experts in computational materials design and materials techniques through our online website as well as our API. We're also committed to showcasing design in the cases where that makes sense for us, but I won't be talking about that today. So I'll start out with the codes. Our earliest code is PyMatchen. It's from about 2009-2010. It is our input and output code that we use to turn the output from various quantum chemistry codes such as VASP, QChem, ABINIT into materials engineering properties that can be understood by anybody who's a scientist and is interested in materials. So the raw output gets turned into band structures, into band gaps, into elastic tensors, and so forth. In order to monitor and control thousands to tens of thousands of calculations, we were also in the need of a workflow code. So in 2011, 2012, we put a lot of effort into designing a workflow code that we call Fireworks that allows us to monitor and divide computations into modular tasks and allows us to make dynamic decisions at any given time whether or not we should reroute that workflow or we should change or add more commands or more modules to the workflow. The codes PyMatchen and Fireworks have recently gotten combined in our Atomate code package. What Atomate does is that it takes routines from Fireworks as well as data from PyMatchen and combines it into recipe-based workflows. Fireworks in itself is completely agnostic to what you're running. You could be running a finite element calculation, but Atomate is actually a code that provides a particular workflow for a particular property. If you want to run a calculation of the dielectric tensor over 1,000 different materials, then you use the Atomate workflow that is designed for that particular purpose. Using these 3 codes, you can actually now, with very little effort and based on the benchmarking we've already done that is documented in our publications, run specific calculations over very diverse structures and chemistries with very few commands quite efficiently. The fourth code that I want to highlight is our API, which allows us to robustly pull a lot of data, you don't want to do that through the website, from the database into the website as well as to particular users. It allows us to analyze that data, uses in PyMatchen, and it allows Atomate to operate upon that data. When we design these codes, we've tried our very best to use best practices from industry, such that all of our codes, except for our website code, is open source. So all of the ones I just talked about are available on GitHub. That allows us to engage users and contributors from all over the world to help us to develop these codes together. Our team is far too small to be able to do this for the whole world of developers and all the things we want to do. So we're very excited about that. We do have the model of benevolent dictators. So we have a couple of people, very, very passionate people, and are willing to devote their free time to managing all the requests to merge into the master branch of these different codes. So the Anubhav Jain at LBNL monitors the fireworks and the Atomate code, and Shiping Ong at University of San Diego and Matt Horton at LBNL monitor the PyMetchen code commits to make sure that they are adequately documented. So every single new module or addition to PyMetchen should be well documented and come with unit tests so it doesn't break any of the existing codes. PyMetchen, as I said, is our oldest code. It has over 100 very active developers from all over the world. It has over 17,000 code commits and is used by over 200 different repositories from all over the world. In just 1 month alone, it gets over 7,000 downloads. This is a success story in the sense that we are able to, this is basically a community effort at this point, and a lot of people are using the code to forward their own research. Fireworks and Atomate are a bit younger, but we're still seeing a nice growth in number of people that are using it, as well as committing back to the master branch. So we have something like 50 total active code contributors. Of course, it doesn't include people who just download the code and use it in their own repo, but people are actually actively developing the code with us. And it powers over 40 code repositories on GitHub. Fireworks is one of the official codes of NERSC, was adopted a couple of years ago as something they are maintaining for their own benefit, as well as those of their users. And that together with Atomate schedules and monitors tens of thousands of compute jobs across our HPC systems. To give you an idea of how these dynamic workflows operate, this is a slide that tells the story if you want to calculate, for example, the band structure or the density of states of a material. You may start with optimizing the bulk structure, which includes a lot of different small tasks that you modularize. So you write the input files, you run the code of your choice, you store the result, and you pass it on to the next firework. Then you do a static calculation, and then you do a line mode as well as a uniform calculation. And all these different parts of the workflow can fail, can have different aspects of reroutes, and this is really what the workflow is monitoring for you, together with a sort of a recipe-based failure recovery mechanism that we call custodian. So using Atomate, you need very little amounts of code and a submission command to run anything from 100 to 10,000 of DFT calculations. Once we have these calculations, whether they failed or not, they get stored in the database with how they finished and what kind of command line that they finished with. When we build a new version of the Materials Project database, we create a number of different databases that contains the different data that we're interested in. So the thermodynamic aspect of all these calculations that builds us phase diagrams and reaction energies, that's one database. The dielectric tensor is another database, and so forth. We call this new modularized database building Emmet, after the Lego movie. We've also decided some years ago, when we started this whole enterprise at the Lawrence Berkeley National Laboratory, to use MongoDB as our data programming language. We actually did SQL before then, but because we found that SQL was less flexible when you're changing the schema or changing how you, what kind of different properties you're including and how they're connected to each other, it was much harder to work with. MongoDB is document-based and easier to change. And if there's one thing that we're designing for in the Materials Project, is change. It's the fact that we're constantly growing and constantly changing the way we connect and do things. Another aspect of our data flow is that once we have all the data in these different distributed databases, we have to decide to do a new data release. And we have a lot of automatic tests in place to do this. We also have manual tests at the very end. So we build these databases, we check for things, for example, how many hulls are broken in the phase diagram builder, we would expect that as we grow our data, the number of hulls to break would probably be smaller, that we have already filled up most of our knowledge in terms of the stable materials, and we're filling up the metastable materials. We generate warnings when we feel that something may have gone wrong, even though the calculation finished. So for example, if we have a large volume relaxation for a converged run, that generates a warning that goes on the website. At the very end, we actually do a differential with our current database as well as the old one to check to see that we don't have large discrepancies, and we figure out where those are coming from. Because we've been up and running for now almost 10 years, we've also gotten to the point where we realize that, of course, there's always going to be development. There's going to be new functionals. There's going to be better ways of doing things, better algorithms. There's going to be faster computers that allow us to run with higher fidelity parameters in our calculations. So we have instituted a deprecation process such that we will recompute some of our older calculations and replace them with newer, better calculations. But while ensuring that our old ones are still there and retrievable through our API for historical record. Even though we have formidable high-performance computing available, there is not an expectation that we will be completely full coverage of all the properties that we are calculating for all the different crystal structures and chemistries. We currently have about 128,000 calculated crystal structures with the very diverse chemistries, but if you look at the property coverage, we're about 13,000 calculated elastic tensors, 6,000 calculated dielectric tensors, and those more compute-heavy properties are not likely to be at 128,000 anytime soon, so it's easier to fill up with structures and chemistries. That's where machine learning comes in very handy, especially given that we have a pretty broad as well as diverse coverage of structures and chemistries already. So we use machine learning to fill in those holes in the data. So for example, if you go and look for an elastic tensor of a particular material and you can't find it, there's a little button to get predictions that is using an underlying machine learning model that will then spit out an answer that guesses based on the previous data and its correlations to those particular data points in terms of chemistry and structure, what the guessed bulk modulus and shear modulus is. What clicking on that point will also do for us is that it will tell us that the community is interested in this particular elastic tensor. So instead of sort of randomly calculating the rest of the world's possible, we will bump up this one to the top of the priority queue, and it will, once we are running more elastic tensors, this one will be prioritized. Another way we are using machine learning is for spectroscopy data. We have over 500,000 calculated K-edge Zanes spectra, which allows us to correlate the spectra and their shapes with specific coordination as well as valence states. So if somebody uploads a spectra to the materials project, which is available online, we will use that machine learning algorithm to guess what kind of bulk structures their spectra is most likely to resemble, and that it is again based on coordination and valence state. And L-edge XFs as well as Zanes is coming. I want to promote the package MathMiner and AutoMathMiner. They're not per se part of the materials project effort, but they're being maintained and driven by Dr. Anubhav Jain at LBNL. And they're a very nice code package in the sense that it helps you to easily retrieve such things as data, to clean the data, which is very important for machine learning again, to do feature extraction from the particular data that you're looking at. Most likely we won't be able to do deep learning. We're going to have to featureize our data and correlate that in order to do machine learning, and then visualize that data and connect that with the existing machine learning models that are available in the literature, such as scikit-learn, for example. So that was a little bit about the codes. I hope that you will find them useful. I'll talk a little bit about data and dissemination. So the current available data on the materials project is something like 128,000 crystalline compounds. We also have molecules and nanoporous materials. But the most important aspect of what we're doing is that we're focusing a lot of our effort on calculating properties of materials. So over 50,000 band structures, over 1,000 phonon dispersion curves with heat capacity and entropy associated with it. I talked about the KX spectra already. Large set of elastic, piezoelectric, and dielectric tensors. This data is very popular because it allows you to do exploration of how these different properties correlate with structure and bonding and chemistry in these materials. And we're seeing a tremendous growth of the amount of data that's being requested through our API, to the point where more than 2 million data requests per day, every day, is our current status. The Materials Project website looks like this. We're actually in the process of redesigning it, so stay tuned. Next year, you're probably going to see something new and exciting. Once you log in, you only need your email address. If you log in, you can choose to look at apps where we aggregate data. So we pull data from different compounds and different properties of compounds and assemble that into things like phase diagrams, Pourbaix diagrams, reaction energies, and so forth. So that's the app view of the world. If you're interested in a particular material, you can click on a particular material. In this case, it's aluminum oxide, and you get a long list of the different polymorphs of aluminum oxide that we've calculated. Here you can see in the list that the ones that are highlighted in green are materials or polymorphs of aluminum oxide where they've actually made. These have been made, they've been experimentally verified, whereas the ones that are not highlighted in green are what we call hypothetical materials. So they may well be synthesizable, but we have no evidence of that today. So they represent candidate hypothetical compounds. Let's say that I click on one of these, then I first get the crystal structure and the calculated lattice parameters. I get things like its potential magnetic ordering, not in this case. I get the band gap, if there is one. I get how stable it is with respect to other phases in that chemistry and so forth. I also get the calculated band structure with associated warnings given the level of DFT. We've also been able to import the topological classification of the Princeton Topological Materials database. We have calculated XRDs. We have the phonon dispersion curves that I talked about before through our collaboration with the University of Louvain and Geoffroy Rotier and Gianmarco Gianese. We have the calculated K-edge Zanes. We have the elastic tensor. And we have substrates. So if you want to try to make a particular polymorph of aluminum oxide, these are the kind of substrates among all the available substrates that are common in epitextual growth. These would be the ones that would promote a particular polymorph in terms of the topological match with the candidate polymorph, as well as the elastic strain. So a minimal amount of strain and a good topological match. We also have equations of state for a small subset of materials. Hopefully more is coming, all depending on computational availability. We have similar structures. So again, grabbing a module from PyMatin, analyzing structures, this data tells you that these are similar corundum-like structures, but with different chemistries. The dielectric properties of the material, and if you have a non-centrosymmetric structure, you get the piezoelectric tensor. The calculational summary comes at the very end, tells you all the levels of DFT that we're using and the different kinds of relaxations. And quite recently, we added through our collaboration with Nomad the ability to download the charge density for our stable materials that are available through the website. So if you click on these icons, then you are sent to a page where you now can get the raw download data of the charge density. And finally, and I want to highlight this, we have user contributions. So there are many people around the world that are calculating or measuring important materials data. So this is where we, through our new module, our new portal, MP Contribs, are able to pull data that has been contributed by other parties, and which nicely sort of connects the different kinds of materials properties that are available in the community. As I said before, over 2 million requests are served every day to the community, to the point where we now have to spin up several different servers to meet that demand. Every year we hold a materials project workshop. So if you're interested in what I've told you and you want to learn more, this is a great way to get educated. It's 2.5 days. It's normally in person, which we really like to do, but this year, for obvious reasons, we're going virtual. We still have 10 to 15 and sometimes more available instructors that will look at all of your different codes and your contributions and work through examples with you hands-on to help you to navigate all these different codes and the ways to use data and to get informed of how to best use the tools that we make available to the community. I talked about MP contribs. I'm very excited about this. This is a way to connect data from different people from around the world. We've opened up MP contribs. You can supply your own data. What you're looking at here is a number of different pilot projects that we supported. It's a very diverse, different kinds of data, from experiments to computations. And once you click on one of these data sets, let's say that you find out about this data in a paper, you want to find out more about it, you go to the data set, you click on it, you explore it, you can see the paper, its metadata. If that contribution has tagged materials project IDs, then you can click on those IDs. That will send you to the materials project itself. And there you can explore more about the particular material that these measurements or this data was computed on. There you see user contributions at the very top of the materials details page. And when you click there, you get to the bottom of the page that I just showed you that lists all the user contributions that are relevant for that particular material. And if you again if you come from the materials project side, you look at this material, you find the user contribution, I think this is really cool, then you can click and find out more. That sends you back to MP contribs, which are actually where the data by the contributor is owned, and they can change that data, they can do whatever they want with it. It's their data portal. We've been leveraging the knowledge of all of our users. We have new user suggested materials. We have votes. Like I said, on the Elastic Tensor, people are actually, by clicking that give me prediction button, they actually tell us what kind of materials data they're interested in. So that's when we listen. User get acknowledged. If you supply your structures to the materials project through the Crystal Toolkit, we will compute them for you. And we will put them up on the materials project with a DOI as well as the user contributed name and provenance. The materials project is used all over the world. This is a snapshot of the user map. You see heavy usage in the North Americas, Europe, and Asia. And as well as we have a number of companies that have come to us and given voluntary sort of quotes that were able to say that this has been useful for them in their acceleration of materials design. We have currently over 130,000 registered users, with somewhere between 2,000 and 5,000 unique users logging into our site every day. I want to thank the Materials Project PI team, and specifically Anubhav Jain and Shuping Ong, who lead 2 of the 3 thrusts that manage our codes, our data, our software infrastructure, our dissemination, and our design of novel materials. And specifically also thanks to all the staff at LBNL, Matt Horton, Patrick Huck, Shamdwar Arknath, and our postdocs Jason Munro and Alex Ganos, who really put their effort and passion into what you've just seen. And with that, I thank you. I thank my group. I thank our sponsors, and I'll be happy to take any questions.